we're going to look then at the calculus of inverse hyperbolic functions. And really, in the syllabus, it come at that in 1 wee minute. We're not explicitly asked this thing, but it's quite nice to see where it comes from. What do we differentiate when we try to differentiate the inverse shine, inverse cosh? Like I said, we don't need to know this explicitly, but once we see it done, then going in reverse is you can see where that's come from. Okay, it's not just sprung out at you. So, for example, imagine we have y equals inverse shine of x. It's not a stretch then to change that to, let's go, shine y, whoops, equals x. Okay, now, if we then differentiate this with respect to y, it's much easier to do. We can differentiate shine y with respect to y and get cosh y. That's what we were doing, at the start of last week and the week before. And when we differentiate x with respect to y, we get dx by dy. Now, flipping that, we then get dy by dx is equal to 1 over cosh y. But this cosh y, we want it in terms of x. We don't want it in terms of y. If we're differentiating inverse shine of x, we want our answer to be in terms of x, not in terms of y. And this is where our sort of identities come in. We know that the cosh squared of x minus shine squared of x is equal to 1. Now, if we want to find out what cosh x is, then cosh squared is 1 plus shine squared. And so cosh x is equal to the square root of 1 plus shine squared x. Okay. So if we apply that here, then we can say that dy by dx is equal to 1 over the square root of 1 plus shine squared y. Okay. Cosh y is equal to the root of 1 plus shine squared y. Now that is quite a cool move, because once we've done that, if you look up at the top here, we've defined x as shine y. Okay, if y is the inverse shine of x, then x is shine y. And so this shine squared y is just simply x squared. And so we can plug that back in and get that's 1 over the square root of 1 plus x squared. And so we can see then that if we start with y equals the inverse shine of x, when we differentiate y with respect to x, we actually get something with no trigonometric function in it at all. It's 1 over the root of 1 plus x squared. Okay. It's the same sort of thing with cosh x. So if we start y equals inverse cosh of x, then cosh y equals x. So instead of differentiating that with respect to x, let's differentiate that with respect to y. So if you think d by dy of cosh y equals dx by dy. And when we differentiate cosh y with respect to y, we get shine y. So shine y equals dx by dy, and so dy by dx is 1 over shine y. Now again, thinking similarly and using our identities here, if cosh squared minus 1 equals shine squared, then shine is equal to the square root of cosh squared x minus 1. And so something similar here, we can say dy by dx is equal to 1 over the square root of cosh squared y minus 1. And again, we've set up at the top here that cosh y is just equal to x. That's what we've put it equal. So this we can change for just cosh squared y, we can change for x squared. And so again, our differential dy by dx is equal to 1 over the root of, x squared minus 1. Let's put that in there. Okay. And so we've got this thing that when we have y equals the inverse cosh of x, when we differentiate that, we get 1 over the root of x squared minus 1. Okay. Now, like I said, we're not explicitly asked to know that, but what we are explicitly asked to know is that if you see a function like this, then we should recognize that when we integrate it, we're going to get an inverse cosh answer. Okay, So when we differentiate inverse cosh, we get an answer in this format, 1 over root x squared minus 1. So the flip is true. So when we integrate something in a format 1 over x squared minus 1, we will get an inverse cosh term. Likewise, when we know that when we differentiate sine to the minus 1 of x, we get 1 over root 1 plus x squared. And so the reverse of that is true. When we integrate something in this format, we're going to get an answer which is an inverse sine function. Okay. So that's just a sort of background from where that's coming. It talks about recognizing integrations of this format. And when you integrate these, you get to inverse sine or inverse cosh. But I want to, essentially, all that we need to do is to be able to recognize, as I said, this sort of format. The integral of 1 over x squared, now we had just 1 there, x squared plus 1. But actually, we can expand on it for x squared plus a squared. Anything squared here. And that'll get you the inverse sine, or I've called it r sine. We know that's, we can write that as the inverse sine of x over a plus c. And this would be the inverse cosh of x over a plus c. Okay, again, just depending on what your formula booklet or the exercise that we're going through, they might put it in either of these formats. Like I say, when you see something, integrate something with 1 over the root of x squared minus a squared, then we're going to get an inverse cosh, term. Like I said, usually, unless you're asked to prove it, you can just quote those results. Okay, and you can compare them so you can find out what A is and so on. We'll see a few examples of that. But sometimes you'll be asked to use a substitution or to prove it. And when you're asked to prove these integrals, then what we're going to do is use a suitable substitution. And those substitutions are this, that where you have the x squared plus a squared, what we do is we let x squared, or the first thing that you're squaring, equal a times sine u. Okay. And if we have something in the other format, which we know is going to be an inverse cosh answer, we let the first thing equal a times cos u. And we'll go from there. Okay. Because what happens is when you put this in, you're going to get a multiple of 1 plus sine squared, and well, we'll see this whenever we go through these examples. So let's have a look where to put it. Okay. So first thing first here, 1 over x squared plus 4. You asked to integrate this. Giveaway, it's in a further maths paper, so it's going to be something along these lines. And we should know then that root of x squared plus a squared, that's going to give me an inverse sine answer. So what do? Well, as a substitution, I'm going to say, okay, let x equal, well, this is 2 squared, so x squared plus 2 squared. So x equals 2 sine u. That's it to start with. Well, if I differentiate that with respect to u, x equals 2 sine u, I get dx by du equals 2 cos u. And just taking that du to the other side, I get dx equals 2 cos u du. And so what we're going to do is we're going to substitute this all in. So for dx, we're going to substitute 2 cos u du. There we go. Instead of x squared plus 4, we now have 2 sine u all squared, which is 4 sine squared u plus 4. Okay. The top line there, that 1 times that gives me 2 cos u. In here then, we know that sine squared plus 1 is equal to cos squared. So 4 sine squared plus 4 is equal to 4 cos squared u. And that's where this substitution is going to earn its money here. Because when we do that, we can find the square root of this, that's 2 cos u. And in this case, cos u divided by cos u is just 1. Dead easy. And so when we integrate 1 with respect to u, we get u plus c. Lastly, again, we brought the substitution u in. We need to put this back into terms of x. So go back up to here. We know that x is 2 sine u. So x over 2 is equal to sine u. And u is equal to the inverse sine of x over 2. Okay. And all we do then is we plug that back in for u, that u is equal to the inverse sine of x over 2 plus c. Okay. So our integration by using substitution that we've learnt in maths and used in further maths before is completely valid here. We just need to be careful as to what the initial substitution is. And that's given in sort of the page above there. Yeah, so is in our last next example, and this one a wee bit trickier. Find, oops, my screen's not showing that. Find the integral of x squared, root x squared plus 2x minus 1. Okay. Guys, this was just a tricky wee one. That where you saw the x squared minus a squared, we knew that or x squared plus a squared, we knew that the integration, or what to plug in for it, the substitution. This one doesn't. This one doesn't look particularly in that format. Other than that, I've got the root there. But what we can always do in this type of thing is then complete the square. So CTS there, completing the square. And where we complete the square in that, we get x plus 1 all squared minus 2. Okay. Which is x plus 1 all squared minus root 2 all squared. Okay, root 2 all squared. Now, in this case, if we let the first thing squared minus the second thing squared, the first thing squared equals root 2 cos u in this case. So again, differentiating with respect to u, we get dx by du equals root 2 sine u, and dx equals root 2 sine u du. Again, we can plug that in. X plus 1 all squared is just root 2 cos u all squared, which is 2 cos squared u. And we've got the minus 2 there. When we multiply this one out, we get 2 sine squared u du, which is 2 times a half of so on. 2 sine squared u. This is what we looked at the other day when we were integrating just and differentiating cos squared and sine squared. When we have an even power of that, then we use the substitution that cos 2x is equal to cos squared plus sine squared. And so we can rearrange this to find that sine squared u is a half of cos 2u minus 1. Okay. So again, that sort of harks back to what we've done before in terms of your substitution. And then that all ends up being the cos 2u. Notes, wasn't it? The previous page. Look, x plus 1 is equal to root 2 cos u. So cos u is equal to x plus 1 over root 2. Okay, that's going back to where we... when we then asked to integrate this further, this is fairly straightforward. When we integrate cos 2u, we get a half sine 2u, and when we integrate minus 1, we get minus u plus c. Now, the only reason I sort of put this one is that there's two reasons. One, there's a substitution there, which probably in this case you'd be given if you're asked to do it. But also it harks back to the integration that we've done on inverse or on cos and sine. But the last thing is this last line here. There's a bit of a stretch to go from here to here. I just need to be a wee bit aware of that. This is sine of 2u minus u. All our original question was in terms of x. So at the minute, that's no use to us. I need to put things back in terms of x. But for sine 2u, I don't know. I've got sine u, yes, I can do that. But sine 2u, I can't do. I can't have a direct comparison back to x. But if you remember our, again, trig identities and our hyperbolic trig identities. Sine 2u is just 2 sine u cos u. And that's 2 cos u times, well, what's sine u? Well, sine u is the root of cos squared u minus 1. So this is the same type of thing that we've done previously. So how do we change sine u to cos u? Just using the double angle formula. Okay. Once we've done that, cos u, we've seen before, is x plus 1 over root 2. That goes back, started to find that. Same sort of thing over here. This is cos squared u, so we get this x plus 1 all squared over root 2 squared, which is 2. Take away 1. We make that all into one fraction. And funny enough, it becomes a perfect square on top there. Sorry, it doesn't actually. It's root x squared plus 2x minus 1, not minus 2x plus 1. But once we've got that done, guys, all of that is then in terms of x's. And so we've got our pretty much our answer. So this is where this sine 2u is coming from over here. U, we can just say if cos u is equal to x plus 1 over root 2, then the inverse cos of x plus 1 over root 2 is equal to u. And so that's where that's coming from, plus c. Okay. But the methods we've used to do this, albeit it's not quite the form of 1 over x squared plus 1 or 1 over x squared minus 1. The methods that we've used to integrate it are fairly similar. Okay, we've used a substitution, and then we've used our cos squared minus sine squared equals 1, and we've used our double angles for cos 2x and sine 2x to be able to work our way through this. Okay, but there's quite a bit to it.